everyone. My name is Thomas Di Martino. I'm a first-year PhD student at Sondra Lab and ONERA, working on topics such as deep learning, forestry, and multi-temporal SAR images. Today, I will present to you all our work for the DSE track of the Data Fusion Contest of 2021, entitled Multi-Branch Deep Learning Model for Detection of Settlements Without Electricity. This work has been developed by myself, Maxime Lenormand is an independent and host of the Mind Behind Maps podcast, and Elise Collin-Koeniger, who is a researcher from ONERA. With our work, we tied for third place in this competition. For visualization purposes of the context of this competition, we display here 5 images of the same scene extracted from the supplied dataset. We quickly notice the wide variety of information contained within all the provided modalities. In addition, each of these sensors seems to have multiple acquisitions, with up to 9 of them for the VIIRS sensor. Thus, it seems to us very important to both consider the multi-modality and multi-temporality aspect of the data when manipulating the dataset. Additionally, the expected prediction image is displayed as a 2D classification map, predicting whether a resolution cell of 500 meters by 500 meters contains human settlements without electricity or not. While this initial dataset is presented as a segmentation dataset, we decided to follow another route by converting this initial task into a classification one. Indeed, the labeling resolution of 500 meters implies that a square of 50 by 50 pixels of every image will have the same and one unique class. Hence, we decided to grid our original 800 by 800 pixels images into 256 patches of size 50 by 50 pixels each. By this process, we obtain a little bit more than 15,000 sub-patches that we then split in 3 folds for cross-validation. The initial dataset is labeled with 4 different classes, among which only one is deemed of interest, and it is the class of human settlements without electricity, here displayed in red. From the decomposition of 4 labels into 2 binary labeling systems with our own distribution, we observe that the presence or the absence of settlements is a measure that is quite balanced, while the presence of electricity, as is something quite rare. And when converting the initial labels to the supplied binary task, we obtain what we display on the right, this sort of one versus all setup, where this one class is the class of interest, and all are the 3 other classes. Well, considering all the presented characteristics of the dataset, we developed this multi-branch model. The main philosophy surrounding this so-called mega model, is just to provide to our neural network different degrees of a priori regarding the input data. It's also good to note a difference between the VIIRS specific processing pipeline on the right of the branches and the rest of the mega model. The spatial resolution of a day-night band of the VIIRS sensor is very low in some sense, and so we decided to spatially average it and only process it temporally using 1D convolutions. To process this time series of 9 acquisitions, we opted for a quite shallow convolutional network with only 2 blocks, each consisting of a 1D convolution, a batch norm 1D, and an ELU activation function. Then the next branch is what we consider to be the simplest. It's just like a pre-trained efficient net B7, pre-trained on ImageNet, preceded by a channel dropout layer that aims to improve convergence despite the high number of input channels, here 89. This branch here, this design acknowledges the heterogeneity between the 3 sensors by splitting the feature extraction process in different branches before merging them at the feature classification level. Each branch combines a 3D convolutional layer, a channel dropout layer, and an efficient net B2 pre-trained also on ImageNet. Here we opted for an asymmetric 3D kernel with a size of 1 in both the height and width dimension, and a higher size for the temporal dimension to extract pure temporal information. Then the last branch is acting as a mix between the last 2 branches. Here we extract first temporal features from each sensor data separately, then we merge them to then extract a texture feature alongside the channel dimension. All these 4 branches are then merged together at a fully connected level before being classified in one of the 4 supplied classes. Well, there exists an ambiguity between the label data and the task that is asked for us, and so we took account for it. We wanted to train our model to both classify input patches into one of the 4 available classes, but also wanted him to understand there's a priority on the retrieval of the class of interest, and so for that we modeled it using a soft F1 loss. So as the F1 score function that is used to score the performance of the model is non-differentiable, we designed here a custom soft F1 loss function where we introduced the concept of soft precision and soft recall, where we basically are working with the probability output of our model as a y hat 1. In addition to a custom loss function, we also developed a particular data augmentation pipeline. We used only geometrical transformation in order not to disturb any data distribution. 2 classical augmentations were used, rotations and flips, but 2 others, kind of more unusual, were also used, such as cut mix, where we cut a small patch within an image and replace it with a similarly sized patch from another image of the same class. Noisy labels was also used, where we randomly offset the aforementioned gridding process to model potentially noisy and inaccurate labels. While we use augmentation during training, we also use it at test time. We transform the image, the initial image to classify, into 4 new images. We merge then every prediction from these 4 images for each fold, each augmentation, by summing the probability value of the class of interest. We then find a satisfying threshold using the best achievable score on the public leaderboard. The final results, all of these, everything we presented led us to reach the following performance with a first place on the development phase dataset and a tied 3rd place on the test phase dataset. While these results are very satisfying for us, we still wanted to dive more deeper into the usefulness of each sensor for the proposed task. Considering the capacities of the day-night band to detect ground illumination, we decided to evaluate it in isolation of other sensors at the task of detecting electrification. In the context of heavy label imbalance, we consider that the performance that we display here are quite satisfying, considering that the F1 score that we used is a measure that takes into account class imbalance, contrary to accuracy. As we have now satisfying results regarding the detection of electricity, we wanted to see how well the day-night band would perform when combined with every other sensor to predict then this time the class of interest. We see in order of improved performance that we have Sentinel-1 and Landsat 8 being outperformed by Sentinel-2. Our idea around that is that human settlements can be found to span over like 20 meters or so, and it could be very challenging to distinguish buildings within the speckle of Sentinel-1. However, we theorize that this could be eased with a deeper temporal stack. So in this contest, we developed a multi-branch architecture that acknowledges the multimodal and multi-temporal structure of the data. We also designed custom training and testing environment with a custom loss, data augmentation, test time augmentation, and ensembling. We studied the contribution of each sensor to the final prediction, showing the capacity of the day-night band to retrieve electrification information somewhat accurately. We also showed the apparent superiority of Sentinel-2 over the other 2 sensors when detecting the class of interest. The central axis of improvement seemed to be based more on a reflection on the type of data aggregated and how to combine them in a physically meaningful way. Among the many ideas we have, we believe that the contribution of time series and radar interferometric products may be of primary interest. At last, we wanted to thank the organizers of the contest for this opportunity to work on such a thriving challenge. We also wanted to congratulate every other participant for their outstanding results and to thank everyone for the exciting development phase and the spine-chilling but exciting test phase. In addition, we wanted to deeply thank our colleagues at ONERA for their tremendous support during the challenge, especially Adrien Chanentong, Aurélien Plier, and Guy Le Bénéreux. And we also wanted to thank you all for attending our presentation. We are looking forward to answering any of your questions.